Hi folks, welcome to Related Rates, Part 5. We're going to take a look at an example that's similar to the last example that we looked at with a tank full of water, but this tank is a cylinder this time and not a cone. And I think you'll find that the cylinder makes it actually a little bit easier than the case of the cone. Okay? So let's get started. A vertical cylinder is leaking water at a rate of -1 cubic feet per second. Now, I know it doesn't say a negative there, but I put it there because I know it's leaking water. If the cylinder has a height of 10 and a radius of 1, so we've got a height of 10 and a radius of 1, at what rate is the height of the water changing when the height is 6 feet? And so if we think about what they're asking us for, it's very similar to the previous problem. They want us to find that dH dt, and they've given us the dV dt. Okay. So let's draw a diagram, let's write some formulas, and get started. So I have a cylinder. I know that the height of the cylinder is 10. I know that the radius of the cylinder is 1. And I'm going to draw a second cylinder just so we can see, like, where is the water at? Because it only fills up to 6 feet, okay? So the height of the water equals 6. Now, last time I said when we moved down the cone, we didn't actually know what the radius was. But in this case, in a cylinder, the radius is still going to be 1. So we actually have a little bit more information than we did last time. Okay, so let's write our equation. Volume of a cylinder is pi r squared h. And we're going to start the same way we started the last problem. I know that if I take the derivative of v, I get dv dt. I know that pi is a constant, so I'm going to leave it out front. And I know that r squared times h means I need to use the product rule. And so let me set that up off to the side. So I will have u equals r squared, du equals 2r dr dt, and v equals h, or dv equals dh dt. Okay, let's put those back into our product formula. U, which is r squared, times dh dt, which is my dv, plus v times du. Okay, let's see what information we have and what we're missing. I have my dv dt, and I'm actually going to write that out right now. I'm going to put it as a -1. And again, the sign was not part of the information, but they told us that it was leaking water, so we knew it was going to get smaller. The pi is a constant, so I know what that is. Do I know the radius when the height is 6 feet? And this time I do. The radius is 1. So I can put a 1 squared there. dH dt is what I want to find, okay? So I'm going to go ahead and leave that as a variable for right now. Plus, the height is 6 times 2 times 1, because the radius is 1. And the radius, well, this dr dt is really asking us, how is the radius changing with respect to time? And we can tell from our picture that the radius is not changing. That means dr dt is 0. Okay. Now when I simplify in this next step, this whole thing is going to go to 0. And I get -1 equals pi dh dt, which means that dh dt just equals -1 over pi feet per second. All right, what does that mean? That means that when the cylinder is losing water, where the volume is going down by 1 foot per second, that the height is going down by -1 over pi feet per second. Okay, let's move on to the next example. Example 9. So this is a new type of problem that we've not yet seen. It says that the angle of elevation is the angle formed by a horizontal line and a line joining the observer's eye to an object above the horizontal line. A person is 500 feet away from the launch point of a hot air balloon. The hot air balloon is starting to come back down from at a rate of 15 feet per second. At what rate is the angle of elevation, theta, changing when the hot air balloon is 200 feet above the ground? And so what we're going to do is we're going to draw a diagram, just like with every other problem we've done. And in this case, we're assuming that our hot air balloon is just going straight up and straight down. It's not moving side to side, it's just going up, and at this moment that we're looking at it, it's coming back down. And the observer is over here. And when they tell us that they are a horizontal distance of 500 feet, they're telling us that the bottom of the right triangle is 500. They also tell us that the angle of elevation is going to be this guy right here. And I'm going to say that x equals 500 because it's a horizontal distance. And that means that I can say y equals 200 because the balloon is 200 feet above the ground. And I actually also know dy dt. Now this balloon is coming down, so negative 15 feet per second. So dy dt equals negative 15. Now what they want to find is not dx dt, but they want to find d theta dt. So that's what's new about this problem. Okay, so throwback to trigonometry. Yeah, I have a right triangle, and I know the opposite side, and I know the adjacent side. Okay, so this is my opposite side, and this is my adjacent side. The trig function that talks about opposite over adjacent is tangent theta. And so I'm going to go ahead and make this y, which is the opposite side, over x. So what do I have to do here? I need to find my derivative of both sides. So the derivative of tangent is secant squared theta times d theta dt. And on the other side, I'm going to have to use the quotient rule. So x dy dt minus y dx dt over x squared. So let's see what information we have so far. I have my x value at 500, so I can fill in that. I have my y value at 200, so I can fill in that. And I also know my dy dt, so I could also fill in that one. One more place I could fill in my x is in the bottom. Now, what I don't know is I don't know my dx dt, but I can actually figure that out from the problem. So this dx dt is how quickly is the horizontal distance between you and the balloon changing? And in this case, it's actually 0 because the balloon's not moving side to side and you are exactly where you are. Okay, we are looking for our d theta dt, which means we want to find this. But what that also means is we need to find this, okay? So let's get started and see what we have. I'm going to go ahead and draw the right triangle off to the side and label some more of the sides. So I have my right triangle. I know this is 500. I know this is 200. And I could use Pythagorean theorem to find this missing side, and I would get the square root of 290,000. Okay. Why is that important? This is my theta, and I know that secant is the reciprocal of cosine, and that cosine involves the adjacent side and the hypotenuse. Okay, so let's isolate our d theta dt first. So I'm going to get x dy dt minus 0 over x squared. If I want to divide by secant squared, that's actually the same thing as saying all of this stuff times cosine squared, because cosine and secant are reciprocal. All right, let's fill in the numbers we have. 500 times negative 15 over 500 squared times cosine of that angle is going to be the adjacent over the hypotenuse, and then cosine squared, so I have to square it. Now that's a lot of numbers to type in. There are certainly a lot of things that you can cancel out. For example, this 500 squared and that 500 squared will go away. And what I really have is 500 times negative 15 over 290,000. And when I type that into the calculator, I will get negative 0.026. Now, because we're talking about angles, we're saying that it's radians per second. Okay. Now, you want to make sure that you've got your calculator in the right mode. And when you do that, you should have your calculator in radians, okay? And so you'll get negative 0.026. And what that means, if we zoom back out for the whole problem, is that when the balloon is coming down, when it's exactly 200 feet above the launch pad, that the angle of elevation is getting smaller by negative 0.026 radians every single second. All right, let's stop there. Come back for one last example in part 6. See you there.